All right, great. So before I throw the floor open for questions in general, there was a question last time about anti-unitary operators. And in particular, if I understood the question correctly, the question was something along the lines of well, let's just go with what's going on with anti-unitary operators. So in a symmetry transformation, where remember that we are trying to keep in our minds, we're trying to juggle in our minds this idea that there are, we will convince you that there's a group of symmetry transformations, there's an abstract group, which is telling us, or is our way of mathematically representing, and I'm going to use that word a few times in a few different contexts, mathematically representing the physical reality of a symmetry transformation in the real world, transformation or translation in time, in space, a rotation. Those are going to be symmetry transformations. Then there's the manifestation of that symmetry transformation. Let me change my words. So there's an abstract group, which is the manifestation of the physical reality of a symmetry transformation. And then there's the representation of those group elements in the Hilbert space that are acting on the abstract vectors that are that constitute our system. Okay, good. And so a natural question is, what are those representations going to look like? And what I claimed without proof is Wigner's theorem, which says that the representations of those symmetry transformations are either unitary and linear operators. Gosh. You have of some element G of some group, or antilinear and anti-unitary. I think the linear and antilinear are pretty straightforward, so I wasn't planning on reviewing that part. But the unitarity, how does that manifest? So we would like to ask what happens under a transformation of states by a unitary operator? Or rather, what happens to the inner product of two states, right? The inner product being what's going to lead us to the physical observables. Physical observables are expectation values, are values for measurements that are actually measured. Let me rephrase that, I'm sorry. So the physical observables are what the numbers can be that you're measuring. So it could be spin up, it could be spin down, it could be the location of a particle. And then the second observable is the probability distribution of those particular values. And that's going to be related to the inner product. And the statement is that for a symmetry transformation that is represented by a unitary operator in the Hilbert space, we have this expression. This is just the definition of the Hermitian adjoint. And then in order for this inner product to be invariant under the symmetry transformation, and that's the idea of a symmetry transformation, physics is left unchanged. So for this to be equal to phi inner product with psi, this is telling us that U dagger equals U inverse. And I think that nobody had any problems with. We're fairly familiar with that. Okay. So then we've got the weirdo anti-unitary. And I would propose maybe if there are any questions, if there's a brief question, we can answer that. There's still a certain amount of confusion. I would say don't worry about it. As I mentioned before, anti-unitarity is only going to come into play for time reversal invariance, the discrete time reversal invariance, which we're not going to cover in this course. It's very important in the standard model, for example, or in our understanding of the universe. But for time reasons, we're just not going to cover it here. Okay, so in this case, what we have is our A acting on phi, our A acting on psi. And the definition of anti-unitary, what we mean by this is A dagger A psi, but this whole object, this whole complex number is complex conjugated. And so in order for us to get something where physics is going to be unchanged, we're going to need that this inner product is not changed too much. Bless you, whereby too much, I mean the inner product is the same up to complex conjugation. And this tells us then that the A dagger equals the A inverse. And the point that you may not be fully comfortable with, but I think you could probably see is that even though the inner product is not exactly the same, it is the same up to a complex conjugation. And you know that probabilities are mod squares. And so the complex conjugation is not going to affect the physics. Yes.
The statement U operator dagger is equal to U operator inverse, we use as the definition for a unitary operator.
Correct.
So does that mean that an anti-unitary operator is also by definition a unitary operator? Because it fulfills exactly the same equation?
Yes and no, right? So yes, A dagger equals A inverse, but what the A does on a state or on an inner product is very different. So,
sure. So
the unitary operator has this property that U dagger equals U inverse, but also when you are acting it on a state ket, you don't pop out the adjunct.
Shouldn't we use that as a definition for unitary?
I'm sorry, you should use what as a definition for unitary?
That first equation that we wrote down.
This.
Yeah.
Well, this is not sufficient.
Oh, right, okay, because it doesn't, okay, no, I understand.
Okay, great, super, yes.
Could you use the left side of the first equation and then the second one as the definition? Like that levels out.
I think that that's equivalent to what we're saying here. So I think that that would be fair if you wanted to. Yeah. Good. Any last questions before we wrap up on this topic? All right. Super. So continuing from last time. So maybe just as a brief review to spin this all back up into RAM for all of us. What I just mentioned, symmetry transformation is a change in a point of view that doesn't change the physics. For any symmetry transformation, there is the identity transformation, or rather, for any symmetry transformation, there's a trivial identity transformation for which the observer doesn't change. In this case, the representation is going to be the identity operator. The identity operator is unitary and linear, so any symmetry transformation that can be continuously connected to the identity operation, such as rotations or translations, that has to be represented by a unitary linear operator. Discrete symmetries can lead you away from the ability to continuously transform to the identity. So a parity transformation is not going to be, if you do a parity transformation, you can't continuously connect that to the identity. All right, great. Then we looked at the infinitesimal transformation around the identity and expanded the unitary operator and saw that the generator of the transformation infinitesimally close to the identity had to be Hermitian and was therefore a candidate for an observable. And then I would say provocatively, or very strongly, interestingly, Weinberg makes a statement that he is unaware of any observable that's not related to a symmetry transformation. That's kind of amazing. Okay, then we defined a group. A group is a set with an operation, has closure, associativity, the identity exists, and inverses exist. And I know you worked with that yesterday in the tutorial. Good, so I think that that's where we were from last time. Let me just pause for any questions on that. All right, super. So what we wanted to do now is we like to prove that symmetry transformations form a group. So suppose a transformation. So what do we need to do? We clearly have a set, which is the set of all symmetry transformations. We have an operation, which is what the symmetry transformation does. We need to prove closure, associativity, that there's an identity, and that there are inverses. So let's first talk about closure. So suppose that a transformation say T1 takes rays Rn to Rn prime. By the way, is it sort of obvious that symmetries are going to be a group, and this is kind of a turn the crank exercise? I'm sorry? Oh, it's not obvious. Okay, then let's definitely do this.
I was taught that the whole motivation behind the groups as an object is mathematically representing symmetries. So
I don't think that that's true.
okay.
The idea of groups is really to abstract away from integers under addition.
Okay.
And we'll see, I'll come back to that in just a second. Yeah, okay, good. So we'll go through this in detail. So suppose a transformation T1 takes rays from Rn to Rn prime, and T2 takes rays Rn prime to Rn double prime. Then performing T1, then T2, which we write as T1 to the right of T2, takes rays Rn to Rn double prime. So i.e. T2, T1 is also a symmetry transformation. As an aside, while I'm thinking about it, I put up, I believe on the last lecture video, a set of additional resources that you could look into. I would say that a lot of what I'm talking about, I talked about yesterday, I'm talking about today, and I will talk about is from Weinberg chapter 2. It's definitely a heavy read. So it could be useful. I hope that it's useful. I hope that what I give to you is more digestible. All right, good. So T1, T2, T1 is symmetry transformation. All right. So similarly, if we think about three transformations where we first have T1 then T2, thought of as a transformation, and then T3, then we'll get the same thing as T1 and then T2, T3. You can go through the various primes if you really want to go through that. So that is the associativity of groups. As we mentioned earlier, there always exists an identity transformation. call it T sub E equals 1. E is often denotes the identity element in a group. And this is just the transformation where nothing happens. We always have to have that. And we can always undo a symmetry transformation. If I walk 5 meters to the left, I can walk 5 meters to the right. If I go forwards 5 seconds in time, I can always go back 5 seconds in time. At least at the particle physics level. All right. So for all transformations T, there exists some T inverse such that T inverse T is equal to this identity transformation. Okay, great. So that concludes the proof that symmetry transformations are groups. I'm going to pause there for just a moment. Yes, there's a question.
Can you write out explicitly what the set of symmetry transformation looks like? Because the way I'm seeing it is that we have these linear maps on the field, and but it's not clear to me how the domains and building into those maps look, because in the proof of closure, we assume that the codomain of T1 is the domain of T2. So I mean, it's not just a set of linear maps like any linear map. You know, it looks like the domain codomain I define in a certain way, so that you can compose these maps. But what does it look like specifically?
Okay, so there's a lot in that question. And my first response, I have a few responses. I would say the overarching response is, let's try to, and I recognize that what I talked about here mixes these things, but let's try to think about the group as an object, and then the representations of the group, which are the operators that act on the Hilbert space. So when you start talking about domain and codomain of the operators in the Hilbert space, that's a separate question that can we get to later when we start talking about the representation theory of Lie groups. And rather, for the moment, can we focus on the abstract group property itself?
Yeah, I'm fine with that. I just don't know what that says. This.
So there's the domain codomain versus a domain of vectors upon which the operators act. And then, so then your question is what's the set of symmetry transformations? And I think depends on the symmetry. Let me give some examples, and then maybe that will help. All right, so we could think about the set of translations, spatial translations in 3 dimensions. And then that group is going to be isomorphic to R3. We could talk about the set of rotations in 2 dimensions. And then your group is going to be isomorphic to the circle, S1. We could talk about the set of rotations in 3 dimensions, and then it's a particularly complicated space that we'll study in some detail in terms of the manifoldness properties. Those are sort of the obvious examples. I'm going to mention in just a second, talking about symmetry transformations that are continuous and discrete. So rotations are a continuous symmetry transformation, but they are a subset of orthogonal transformations. And orthogonal transformations include, let's say we stay in the Euclidean metric, they include a parity transformation. And then the group manifold is more complicated because we have the manifold that is continuously connected to the identity and a completely separate manifold, which has the parity reflection of the identity and rotations about that element. So those are several examples. Seth, do you feel like that is helpful for you in your question?
I just wanted to know if it's possible to write out the set that's associated with group in explicit way.
Yes, and let's get there. So maybe just as a preview, so the set for rotations in 2 dimensions is going to be 0 to 2. The set for translations in 3 dimensions is R3. Yes.
What's the closure, what you said for the closure part?
Yeah.
So T1 takes rays from R into R in prime.
Yep.
And then T2 from R in prime to R in double prime. But so that is it, I don't know how to phrase my question. If T2 were to not be from R in prime, so if it were to be from somewhere else to R in double prime, then okay.
I think it's a different question.
It was, I kind of did give them would it still be like closed? Yeah.
Maybe the issue we have is that the reason we want that explicit representation of the set is because it's not obvious to us how we get the you know what I mean?
Yeah. So can you maybe just so I hear your questions, I hear your confusion. I feel like examples are going to make this much more clear. And can just for time reasons we park this for now, and then come back to it if it continues to be an issue. Okay, great, super. All right. So as mentioned, symmetry transformations. We'll consider fall into 2 categories. Continuous and discrete. And for the continuous transformations, that we'll mainly focus on. No, that we will purely focus on. Well, mainly focus on. We can add additional critically valuable mathematical structure on our group. That technically the group be a smooth differentiable manifold. So, if you haven't done differential geometry, that's not a problem. Really, all we're saying is, i.e., we can perform calculus on the group. So we can take derivatives of functions of group elements. We can take integrals over functions of group elements. And in fact, when we talked Tuesday, about having looking at the representation of the operators or near the identity, we already assumed this differentiability property to do an expansion in the real parameters for small real parameters. Okay, so a smooth manifold obeying the group properties for which the group operation is differentiable is a Lie group. I'm sure you've heard of Lie groups before. Now, why are Lie groups so important? Why are Lie groups very important? The connection between symmetry transformations, rather continuous symmetry transformations, and Lie groups was the subject of Hilbert's fifth problem, whose solution basically was that, yes, all continuous symmetries are related or are realized as Lie groups. As physicists, we would like to have translations in space, translations in time, rotations. When we get to special relativity, we like to have boosts. So all of these symmetry transformations, which we encounter all the time, and that as basically the fundamental working principle of modern physics is that the symmetry drives physics, then tells us that we need to very carefully study the mathematical properties and the physical consequences of Lie groups. Okay. All right, so we're therefore interested in the unitary representations of Lie groups. I'll give you a formal definition of a representation in a moment. But we talked about unitarity already, and you see the connection to unitarity because of symmetry transformations, the identity, and Wigner's theorem. And in particular, we can characterize the possible particles or states of our theory by the irreducible unitary representations of the symmetry group of the problem. What we'll see, for example, with SO3 is that if your problem has a spherical symmetry, then the types of particles, the types of states that your system can have is highly restricted. That, for example, I think you know at least from high school chemistry, if not undergraduate physics, that you have spins that are half integer, 0, half, 1, 3 half, so on and so forth, and nothing else. And that's pretty amazing. Okay, very good. So with that as a motivation, we need to understand irreducible unitary representations. What does that mean? So what's an irreducible representation, which is often called an irrep for short? All right, so we're going to get into some math some just definitions of things in order to be precise. My feeling is that this is not going to be too deep of a dive. But especially those who are less theoretically inclined, sort of give me a sense. All right, so let's first define a group homomorphism. Which is a map. Call it little h from group G, capital G, to group capital H between two groups. So we have the first group, which is some set of elements, and there's some operation on it, which I'll call star. And the second group is a set H with some operation, which I'll call open circle, such that for all A and B in G, H of A star B is equal to H of A open circle H of B, i.e. the group homomorphism preserves the group structure of G in H, right? Basically, the most important property of a group is the group multiplication table, where multiplication I'm using is sort of or group operation table. Like what happens with integers under addition, you need to know how one integer becomes another under addition. And you can find a group homomorphism between integers under addition and the real numbers under multiplication through the exponential map. And so you can work with either of those groups. Well, let's not get ahead of ourselves. Good. So we preserve the group multiplication structure. Great. So an isomorphism is a bijective group homomorphism. So what does it mean to be bijective, i.e. one-to-one and onto, injective and surjective? So i.e. both H and H inverse are group homomorphisms. If an isomorphism exists, then G and H are called isomorphic. And the two groups differ only in notation. And are identical for all practical purposes. All right. So it's often useful to have examples. There always exists a trivial homomorphism between groups what do you think would be kind of the dumbest thing that you could do that would necessarily preserve your group multiplication property? There you go. Well, the identity map or map everything to the identity?
No, the identity.
Well, what does the identity map mean if you have two groups that are very different? So I could have,
Oh, well, maybe mapping itself. Isn't that the identity?
so I would like to have, so you could do, yeah, so if you have the group, if the map is between the group and itself,
Yes.
then I 100% agree with you, then the easiest thing to do is just the identity.
Okay.
But I'm thinking more generally that I have a group and then not necessarily the same group. So you could think about, for example, the complex plane, and you have some function that is a pole in the complex plane, how many times you go around that pole on some kind of a contour. And so a natural mapping between groups would be the group of integers under addition, and then the group which is these curves that go around this pole, and then can be continuously deformed without crossing the pole. Okay, so let's try that again. So what's sort of the dumbest thing you could do as a map between two groups from one group to another group? Yeah, map everything in the group to the identity, right? So everything on so H of A star B is going to be identity, H of B is the identity, H of A is the identity, so it's always going to be identity to identity, so that will always work. So for all elements of our group, the map of that group element gives us the identity element in the other group. Okay, so another example, I've mentioned this before, the exponential map. Between the group, which is the real numbers under multiplication. What am I doing here? Oh yeah, so the real numbers under addition and the group, which is the real numbers without zero under multiplication. All right, great. So a representation which I write as pi, little pi and big V of a group. Big G is a homomorphism which is taking some element G of the group into pi of G, which is an element of the general linear group acting on the vector space V. So GLV is the group of invertible linear maps that take V to itself, with V a vector space. Right. So a Hilbert space is a vector space. So for us, in terms of the physics, the V is going to be a Hilbert space. A representation is faithful if it is injective. I.e. 1-to-1. And the point is that you're not throwing away any original information from the group. Right, so mapping everything to the identity is not a faithful representation. We've lost something very important there. When V is finite dimensional, and a basis for V has been found or has been chosen, then linear maps, linear invertible maps. And matrices with non-zero determinant can be identified. So we have that this GLV is isomorphic to GLNC. Right, so this GLNC is a set of all n by n matrices with complex, what do you call the entries? Complex entries with non-zero determinant. Why am I insisting on non-zero determinant? Yeah, so the matrices are invertible. All right, super. An irreducible representation is a non-zero representation pi v of a group that has no proper subrepresentation. Remember that a subset of a set could contain the set itself, could be the set itself, but a proper subset is smaller than a set. All right. So no proper subrepresentation, which we say pi, say restricted to W on the vector space W, where W is a proper subset of vector space V, closed under the action of our representation pi, the set G is a set such that G is a G. All right. Super. So we're setting up for ourselves this structure, right? That we have this abstract group, which is manifesting mathematically the symmetry, physical symmetry transformation. And now we're setting up the mathematical structure to take any element of that group into the unitary linear operator that acts on the Hilbert space that our quantum mechanics lives in, or that our state in quantum mechanics lives in. Okay. These are more or less all definitions, but maybe I can pause here, either for people to catch up or if there are any questions. Okay, I don't know if you've looked at the cover of the Sakurai book, the red Sakurai book. Fair enough. Well, okay. So now, like, how do I, like, I read this great comic the other day. Let me describe to you in words the visual comic, and this will go very well. But anyway, so if you do get a chance to take a look at the cover of Sakurai's book, what I'm about to talk to you about will make, will draw a direct connection. Okay, so every finite dimensional unitary representation is the direct sum of irreducible representations. What is a direct sum? So given representations call them pi1 v1 and pi2 v2 of dimensions n1 and n2, there is a direct sum representation of dimension n1 plus n2, denoted pi1 circle plus pi2, and then v1 Cartesian product v2, given by the homomorphism, which is pi1 direct sum pi2, taking some element of the group into pi1 of G and then pi2 of G 0, 0, where I'm thinking about this as a matrix where I've already chosen a basis. You don't need to choose a basis to define a direct sum, but it's sort of easiest to visualize as matrices. So therefore, direct sum representations are what's known as block diagonal. Right? I have here some n1 by n1 dimensional block. And then I have here an n2 by n2 dimensional block. And neither do these blocks speak to each other. Just a second. So going forward, if we think about a problem with rotational symmetry, we could imagine that there is some part of the system that is represented by a particle with spin 1/2. And that'll be a two-dimensional vector space. There might be another part of the system that is represented by a spin 1 object. And when this system, this quantum mechanical system, undergoes some kind of a symmetry transformation, then that spin 1/2-ish thing, its components get all mixed up. Spin 1 thing, all its components get mixed up, but they don't get mixed up between each other. And that's really what we mean by a particle. It's something whose properties don't change under certain symmetry transformations. Yes.
I wanted my two irreps, they reduce the
Yes.
Okay.
Well, in general, they don't have to be. They could be just representations.
Okay.
But because of what I just said, like if they themselves are not irreducible, if they themselves are reducible, precisely, you'd have yet further block diagonality within here. And so this is the motivation for why we seek the irreducible representations. These are the fundamental building blocks for the representations which are going to allow us to effect symmetry transformations in our quantum mechanics. Good. Very good. I think that's what I just said. All right. Okay, so hang on to your hats. That's all well and good. And maybe because I'm going to say hang on to your hats, let me pause and see if there are any last questions about what we just talked about. Because it's going to get now irreducibly complicated, more complicated, which is not me being the nasty theorist I would like to think, but is just the nasty nature of the universe. Which is to say that, as I've said several times before, so it's important, I want to emphasize it, so I'll say it again. the physical observables are insensitive to the phases of our states. So when we have these symmetry transformations acting on a vector space, what's important, what's physically different is when you go from one ray to another ray. But within a ray, you have this complete insensitivity to normalization and overall phase. And this causes a wrinkle, which is that we need to expand our types of representations that we consider. So far, we've considered representations that are exactly a group homomorphism. But what we need to allow is we need to allow this flexibility in phase. So we need to allow the possibility that if we have the representation or the representation, well, the unitary operator for one group, one symmetry transformation, followed by the unitary operator, the second group transformation or symmetry transformation, that we get the unitary operator for the third transformation, which is G1, G2, and then an extra phase. And these are known as projective representations. I'll write this down in a section. And you're probably thinking, oh my God, why do I care about this? And in a fundamental way that is literally giving me shivers at this moment, I would love to not have to think about these objects because they're hard. And if these objects didn't exist, but if these objects didn't exist, we would not exist. Because in fact, the integer representations of SO3, spin 0, spin 1, spin 2, those are ordinary representations. The bosons are ordinary representations. But the half integer spin representations, a half, 3 halves, 5 halves, the fermions, those are projective representations. So if quantum mechanics did not intrinsically require projective representations, fermions simply would not exist. It's a necessary consequence of the topology of SO3, which we'll get to in real detail. Okay, so with that as context for, I'm sorry, something that's going to be a little painful, I'm going to give you the pain. All right. So there's a wrinkle in the above story. Recall that in quantum mechanics, we're only interested in transformations of states up to distinguishable rays. I.e., or in particular, we must allow for the possibility that the unitary operators that effect a symmetry transformation on the vector space live in a group representation up to a phase, i.e., we can have projective representations. That's the technical mathematical term. So now we have our operators or our map, which is the U, and then our vector space, which is the Hilbert space. So, map. Map. And this is our Hilbert space. Such that we have some, let's make this more obvious, unitary operator effecting transformation T1, followed by unitary operator effecting transformation T2, that this is the unitary operator for the group element T1, T2. So everything looks good, everything looks like a group homomorphism, except that we add in an e to the I 5 that depends on, or can depend on T1 and T2. Oops. We'll find that the half integer s equals 1/2, 3/2, etc. UIRs, unitary irreducible representations of SO3 are projective. Okay. Maybe let me pause there for any questions on this fairly abstract and at this point perhaps not very concrete material, conceptual material. Where the plan after this is to go through in detail examining rotations in 2 dimensions and determining all of the unitary irreducible representations of SO2. Yes.
So we all can set
that's certainly the goal. Yeah. I mean, otherwise it's.
So you don't want to do something.
Yeah. No, for sure. And again, I regret that you don't have some previous experience to hang your hat on. But this will hopefully be self-contained. And again, as I go through the example, please be very active in asking questions as you haven't necessarily seen these kinds of things before. Yes.
What is the word?
Let's go. It's okay. No, go ahead.
What is the word after section 4 of the last line?
UIRs?
Oh,
unitary irreducible representation. Yep. Good. Great. Oh, funny. So I said that very slowly. UIRs, and I said unitary representations. Yeah. I think it suggests, I was a bit ahead of you folks. I'm sorry? Got it. Great. Yep. So these are as I mentioned before, and fine. These are the fundamental building blocks. So these are the things we will find. Yeah.
So for full discipline,
those are ordinary. So what one will find for integer spins is that UT1, UT2 gives a UT1, T1, T2. Yeah. So exactly. So I would say clearly projective representations are a generalization of ordinary representations. Yeah. And I would say somewhat mercifully for SO3, this phase can only take 2 values, 1 and -1. And what one will find is that roughly speaking, under a rotation by 360 degrees, an electron state, for example, turns into minus the same electron state. And there was some question for a while whether this phase was even observable. But through some very clever beam splitting experiments, one can precisely observe the projective nature of the representations of spin on that. Yeah.
Okay, I'm just trying to comprehend this rainbow. So
Okay, sure.
we want these transformations of these operators to be insensitive to phases.
Well, it's not that we want the operators to be insensitive. It's a recognition that quantum mechanics is insensitive to the overall phase of the vectors that live in the Hilbert space. And that instead of a nice, pleasant, the topology of our vector space, of our Hilbert space, is not pleasant. It's rather a complex projective space. And so that means that there's a lot of information that gets modded out, would be one way to phrase it. You remember that there's that equivalence relation that we talked about, which is basically the normalization of any particular state. And so what that means is that when we talk about the mapping of our group elements of our abstract group, which itself is what is realizing the symmetry, the physical symmetry transformations. When we look at the maps from that group into the operators acting on the Hilbert space, then those operators, by Wigner's theorem, have to be unitary and linear for the part that's connected to the identity, continuously connected to the identity. And you would think that the multiplication property of the operators in the Hilbert space should reflect the multiplication property of the group elements. And they do almost.
So it's, we're trying to encode that insensitivity to the phase in the group as well.
Almost. So it's not that we're trying to encode the insensitivity of the phase in the group. It's rather that when we examine the potential or the possible maps from the group to the operators or to the operators that act on the Hilbert space, we have to allow the flexibility in the phase. So as much as we may wish we don't have to think about this generalization, the physics demands that we allow for this kind of generalization of a representation. What's amazing is that Ken, the shivers, it's crazy. Like Cartan thought about this stuff before quantum mechanics. He was just like, cool, representations are a thing. Let's like just think about the slight generalization and invent projective representations. And it turns out like it's the fundamental building block to all of 20th century physics, roughly speaking. Cool. Any last questions? It's a lot to hold in your head. It's a lot easier for me because I've been doing this for a long time. But I certainly remember being confused by this and spending a lot of time on Stack Exchange. Really, and it's a great resource. So I encourage you also to look at it. Which is me, a long way of me saying, just keep asking me these questions. It's okay. Like I suspect we're gonna have to say these things over and over and over again because it's just super new, super different, really abstract. But hopefully I'm gonna give it to you in a digestible way. And then we'll go into an example. All right.
The risk of being is not with respect to it, but it's what happens, and now we have to deal with it.
I think that's fair, yeah. And I would rather not have to deal with it, but too bad. Yeah. If we want fermions, then this is what we got to deal with.
The expected value, you do the product and then you test it in our representation of maps.
Yeah. Yeah. Good. Okay, so let's talk about rotations in 2D. And this problem is ultimately going to be a little bit disappointing because rotations in 2 dimensions are abelian, they're commutative. And there's a theorem that we'll talk about, which says then that all of the unitary irreducible representations are one-dimensional. So it's going to be kind of boring. So I'm just saying that right now, because it's going to be a while to get to that point where we've computed all this stuff. So don't get your hopes too high. I want to set your expectations low. Unlike when Star Wars Episode 1 came out and our expectations were very, very high. I went to see it and we were very disappointed. What I want to do is I want to set your expectations very low, and we get to the end, then hopefully you're either like, or maybe you're like, oh, that's actually pretty cool. And then when we get to SO3, things are going to get really interesting. But the idea is to start with not SO3, so you have some other example, which is in fact in many ways simpler. And then we will generalize from SO2 to SO3, SON in general. Cool. All right, great. Notations in 2D. All right. Suppose we have a vector. X vector element of R2. And we rotate our coordinate system. Sorry, let me think about this. Unbelievable that I like the first sentence I'm tripping up on myself. And we rotate our vector. Counterclockwise. No matter how many times, I swear, no matter, and you will find this when you become academics yourself, no matter how many times you read your notes for your lecture, you're like, I got it down solid. You start lecturing, it's like, oh man, what am I talking about? All right, so we rotate our vector counterclockwise by theta degrees. So we have that x vector prime is some matrix. So I'm doing sort of like a left-right arrow, and I call it R inverse acting on X. So according to my notes, and hopefully we can reproduce it, think about some vector X in this coordinate system where I have components of this vector X, which are X and Y. Then the new components after the rotation so prime y prime. So my x prime y prime, this is equal to cosine theta, sine theta, minus sine theta, cosine theta, acting on xy. And if I look at this, I can immediately see that I've got my signs flopped as far as I can tell, because my x is decreasing. So my x prime is smaller than my x. So I had better this to a plus to correspond with whatever. So hence our group G is a set of all, say, R matrices, which are cosine theta, positive sine theta, minus sine theta, cosine theta. Such that theta is an element of 0 to 2 pi. So remember, our group is a set of elements. So in this case, the elements are these 2 by 2 matrices, but it also comes with a group multiplication operation. In this case, the group multiplication operation is matrix multiplication. Just a second, just a second, just a second. Which is multiplication. Yes, the signs are swapped. So I'm defining the transformation in terms of R inverse. And so here this is R. Yeah, no. Good question. Yes.
Why conservation?
Active versus passive transformations, which we will get to when we talk about the Schrodinger versus Heisenberg pictures. I mean, at some point in class mechanics, you've talked about active versus passive transformations. Okay, then let me just briefly, one sentence, right? So we can think about two possibilities for a symmetry transformation. We can actively rotate the vector, or we can passively change our coordinate system. Good. All right, great. So in terms of our Lie group, remember that our Lie group has this extra structure. So we have a group, we've got a set of elements, and we've got a group multiplication property, but what's the manifold upon which we are performing, we will be able to perform calculus. So notice that the manifold for the group is given by the parameter theta that uniquely specifies the group element, right? I can rotate a vector anywhere between 0 and 2 pi. And once I tell you, or once you tell me how much you want to rotate the vector by, that gives me the group element. Great. The manifold is one-dimensional. There's only one parameter. There are two parameters, two-dimensional, so on and so forth. And is topologically non-trivial. It's a fancy pants word for saying that theta equals to 2 pi is identified with theta equals 0, right? The real numbers go from minus infinity to infinity, and none of them are the same as any other. But a rotation by 3 pi is the same thing as a rotation just by pi. So that's a topological non-triviality. So the group manifold is S1, the unit circle. Since S1 is bounded, i.e., theta is definitely never infinite, right? It goes from 0 to 2 pi. Let's just write it this way. I said before, theta goes from 0 to 2 pi. The group G is compact. Remember that mathematically, compact means closed and bounded. We're getting more mathematical terminology. I apologize, but it's actually, compactness is very important because it's only the compact groups for which the unitary universal representations, for which you are guaranteed the unitary universal representations are finite dimensional. So if you think about translations in R3, or very importantly, when you have Lorentz transformations, those groups are not compact. And so the nice things where we're going to get the representations of our group elements being, 2 by 2 matrices, 3 by 3 matrices becomes much more complicated. Okay, good. If we examine the results, of 2 rotations, say we have g theta, which is cos theta minus sine theta, wait, we did, sorry, let me be consistent with my signs. Cos theta, sine theta, minus sine theta, cosine theta, and then g phi, which is cos phi, sine phi, minus sine phi, cos phi. Then if we rotate by phi, then rotate by theta, trig tells us that we get cosine theta plus phi, sine theta plus phi, minus sine theta plus phi, cosine theta plus phi. So I'm simply writing this down, but really what I'm doing in the background is I'm multiplying those matrices out and applying various trigonometric identities. But importantly, if I were to do that same procedure of multiplying the matrix, giving rotation by theta, and then a matrix multiplied by the matrix giving rotation by phi, do my trig identities, I'm going to get back exactly the same rotation matrix here. So, i.e., the group is commutative. And we call the group abelian. All right, super. Notice that this G that we've been talking about is already some subset of the linear invertible maps in 2 dimensions with real entries. And hence, G is already a representation. The defining representation. So now we have Jack's identity map. The identity map is the representation map. Yeah, good. All right. So what we'd like to do, in what we always tend to do in math, is we tend to abstract away, right? So we started with this concrete idea of rotating vectors in 2-dimensional space. But what is the fundamental property that is crucial for our understanding of what rotations mean? And to abstract away from rotating a vector, we see that the hallmark of rotations in 2D is that they leave the dot product invariant. That if I have some vector v1 dotted into vector v2, and then I rotate both vectors by the same angle theta, v1 prime dot v2 prime is equal to v1 dot v2. I want to take a moment, so let's keep our inner products separate, right? We've got inner products living in our Hilbert space, and we want to have that our symmetry transformation leaves that inner product invariant. But that inner product is going to looks very, very different in general from just this simple 2D vector product in Euclidean space, right? We might have that the dot product is the integral of function, complex conjugated function. Or if we have some finite dimensional vector space, it's the sesquilinear, v star dot v dot product. So this is a different dot product, and we are interested in Yeah, just ignore the inner product of the Hilbert space. What we're interested in here is the Euclidean two-dimensional dot product, and that is invariant inverse of the transformation for rotations. Good. All right. So the most general transformation that leaves the scalar product, leaves the Euclidean scalar product invariant satisfies, so v1 dot v2 is equal to v1 prime dot v2 prime, which is equal to our vector v1 hit by the transpose of our transformation that is hitting the v1, I'm sorry, the v2, right? So my v2 prime is some matrix hitting v2, and then that means that the transpose is hitting the v1, because we're thinking about the v2 as a column vector and the v1 as a row vector in this matrix multiplication way of thinking about the problem. And in order for v1 dot v2 to be equal to this nasty thing, then clearly we need that O transpose O is equal to the identity. I.e. this O is orthogonal. Literally the definition of orthogonal, an orthogonal matrix is a matrix that satisfies this condition. Okay, notice that, whoops, what I have written here makes no reference to the number of components of any of these vectors. So this is completely general. So abstracting away, the orthogonal group ON in n dimensions is the group of invertible transformations preserving inner product. Well, I would say preserving the Euclidean inner product on a real n-dimensional vector space. And ON is isomorphic to the group of real n by n invertible matrices O satisfying O inverse, I'm sorry, equals O transpose. ON corresponds to a continuous symmetry group and is therefore a Lie group, hitting the Lie group again. The idea of hitting the concept of a Lie group again is that the various things that we're going to do here for O2, well, SO2, and then ultimately for SO3 is completely generalizable to any Lie group. So I'm giving you a set of techniques with broad applicability. Very, very powerful tools. Okay, let me just pause there for a moment. Any questions? All right, super. Yes.
How can we, or add correspond to
Because it's going to be a subset of ON is going to be rotations and dimensions. And that's going to be a continuous symmetry group. I can think about like the rotations aren't discrete. But I can rotate by nothing and I have the identity, and I can rotate by as little as I want.
so when we all
If you give me a moment, I'll prove to you that you cannot reach all elements of ON continuously from one to another necessarily.
and that's not a problem.
Correct. You could think about, okay, so the calculus that you know and love is on Rn, and you could think about some subset of Rn, in which you have some function, and you can do calculus on the function, and then you have some little like Balabi area of Rn, and then imagine that you have some other Balabi area of Rn that's disconnected, and that function's also defined on that other area, Balabi area of Rn. You can still do calculus over there. You just can't continuously go from each Balabi, from one Balabi area to another Balabi area. And that's going to be completely analogous to what we're going to have here. Cool. Any other questions? Thank you. Good question. Okay. All right. Super. Let's continue. So notice, so let's talk a little bit about topology of ON. Briefly, notice that for any operator O that's hanging out in this ON group, we have that, so 1 is the determinant of the identity matrix. That's a true statement. We know for an element of ON that, I guess I could go step by step. One can write the identity matrix as the O inverse O, but because it is orthogonal, O inverse is O transpose. In general, the determinant of two square matrices is a determinant of one multiplied by the determinant of the other. And in general, the determinant of a transpose is a determinant of itself. So therefore, the determinant of O must be equal to plus or minus 1. And coming back to the original question, the previous question, this is where we see the disconnected nature of the two sub-manifolds of ON. So ON is made up of two disconnected submanifolds. One submanifold is smoothly connected to the identity matrix. With determinant plus 1, which preserves the orientation of an orthonormal basis. For our vector space V. The other submanifold has determinant -1. And elements are smoothly connected to the element that generates reflections. Generates a reflection, let me put it that way. If you have, more than say 2 dimensions, you can have different reflections. You could say in X, Y, and Z, you could reflect across X, reflect across Y, reflect across Z. The point is that choose one of those reflections, and all of those other reflections are a reflection followed by a rotation. So we just need one reflection. Yeah. Yeah, exactly. Yeah. Good. The Lorentz group is more complicated because in addition to a spatial reflection, you also have a temporal reflection. And because the metric is not, because the metric cares about whether you're time or space, those are different. And so the Lorentz group is actually has 4 disconnected components, whereas the orthogonal group has only 2 disconnected components. Super. So we've got, as I mentioned, these two disconnected submanifolds. I've been careful to call them submanifolds. Why is that? Is because the submanifold that's smoothly connected to the identity is a group. You have to have the identity element in your set in order to form a group. But the submanifold that's smoothly connected to the -1 or to the reflection, that is not in of itself a group. It's only a group once it's considered in addition to its disconnected partner. Okay. So this set devoid of the identity is not a group, not a subgroup. Okay, so the proper subgroup of orthonormal transformations with determinant +1 is known as the special orthogonal group. In n dimensions, or SON. This is going to be true in general, right? So we started with our group ON, and by restricting to determinant +1, we add the S in front. We'll encounter UN, and then the subgroup of UN for which the determinant is +1 is SUN. Yes, question.
Why do you say a proper subgroup?
So proper means that it is legitimately or actually smaller. There are elements there are actually fewer elements
Oh,
in,
not necessarily equal in what? Okay, yeah, okay, okay.
and in fact, it's not that it's not necessarily, it's necessarily smaller, it's proper.
Yes, yes.
Yeah, good. And so we're dropping that disconnected submanifold. Okay, good. All right. Good. So we see that our symmetry group of rotations in 2D is isomorphic to SO2. So we're going to study SO2. We're also going to be interested in SO3, the proper subgroup of orthonormal transformations in 3 dimensions. Okay. Now, let's melt our brains a little bit, potentially. What is the dimension of ON, which is going to be equal to the dimension of SON? So, i.e., how many dimensions does the manifold of SON have? I.e., how many parameters are needed to uniquely specify a group element in SON, i.e., yet again, how many generators does SON have? We could go even further and ask, how many conserved quantities could you have associated with a symmetry group? Okay. Yes.
Or is that in this case, that is length?
Is that just the lengths? No, and let me go forward and then maybe we'll circle back. Okay. So if in general, an n by n matrix or not if in general, it's not if in general, it is in general. So in general, an n by n matrix has n squared free parameters. Right, you have n squared different entries in your n by n matrix. The restriction that O transpose O is equal to the identity imposes imposes constraints on those entries. In particular, we have O transpose O. This thing has got to be equal to a matrix of ones down the diagonal and zeros everywhere else. And my claim is that it's the upper right triangle of entries that completely restricts the free parameters of the entries of the O transpose O. And why is that? If I consider the transpose of O transpose O, this is again equal to 1's down the diagonal and 0 otherwise. So the upper right triangle of the identity gives these constraints. And there are, okay, so I have n entries down the diagonal, and then n minus 1 entries of the next diagonal column up, diagonal row, I don't know what to call it, and then it'll be n minus 2, blah, 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 all the way down to n, or sorry, not down to n, down to 1. There are n plus n minus 1 plus down to 1 of these constraints. And n plus n minus 1 plus blah, 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 all the way down to 1. That sums to n times n plus 1 over 2, according to my notes. And according to Gauss when he was like 8. What an unbelievable genius. Okay, so therefore, the dimension of ON is going to be equal to n squared minus n times n plus 1 over 2. And so that's going to be n times n minus 1 over 2. You see that I got my n squared, I got an n squared over 2, giving me an n squared over 2, and then I have a minus n over 2, so I get the minus 1 there. So this is the dimensionality of the Lie group, which is very different from the dimensionality of the vector space upon which these rotations are occurring, or not necessarily the same. So for n equals 2, we get 1. It's only the angle theta that we need to worry about. For n equals 3, we get 3. The way you can think about that is you have two numbers that specify the vector about which you're rotating, and then one number which gives you the amount of rotation. So that's 3. So in 3 dimensions, it's kind of special that the number of components of the vector, or rather the dimensionality of the vector space is the same as the dimensionality of the manifold. But if we go up to, say, n equals 4, then we're going to get 6 dimensions for our Lie group, and only 4 dimensions for the vector space, and so on and so forth.
I was going to ask, it's not really, further up is the dimension of ON is the same as the SON.
Yes.
How does that, with SON, we've got like the additional constraint, that's 2 plus 1.
Uh-huh.
How does that always get constraints in that?
Very good, because your problem set yesterday was determine the dimensionality of SUN, and that determinant being 1 killed a dimension, right? But there you have a continuous phase. And so you get, that's going to really kill a dimension, whereas here this is a discrete difference, right? So if I think about SON versus ON, the only difference is I'm removing this disconnected manifold. I'm not reducing the number of dimensions of either of those submanifolds.
So reducing the dimensions is throwing out the.
Yes.
Okay.
Yeah. So that's a key difference that I wanted to emphasize between SUN and SON. Yes.
Also relating to yesterday.
Yeah.
The entries would be complex. Yeah.
For UN, yes.
So for ON, are they always real?
So the short answer is yes, they're always real. A slightly longer answer is think about what the ONs are doing. right? It's always good to, for me, I think for most people, to go from the abstract to the particular to ground ourselves. And we're, in a way, certainly with the SON specifically, we're thinking about rotations of real vectors. So we're thinking about rotations in the world that we see around us. And so we're going to restrict how we transform those vectors, certainly to, they have to go from real entries to real entries. So we're not going to allow our matrices to have complex entries. Good.
Also, to preserve dot products, you can't have any minuses with the dot product, right? You're like from parts.
I think that's quite true. Right, so so let me continue. All right, good. Because we've talked quite a bit about ON, and you did a homework problem on UN. Let's talk about UN a little bit. All right, so while discussing what are known as the classical groups, and group theory is a rabbit hole with no end, but it's deeply enriching. And you would think that there's an enormous, uncountably infinite number of classical groups, but they're actually very few. There are very few Lie groups. Most of them are the SONs, or rather the ONs and UNs. And then there are some exceptional groups, and I'm missing some I know for sure. Go to Wikipedia. But one thing that people do, because there's such a small number of them, and I think you probably know just from the ether that the gauge groups of particle physics are of the SUN type. And we're thinking about abstracting away and making bigger and bigger groups. People have thought about, well, maybe there is, because there's so few Lie groups, maybe there's a bigger Lie group that contains the SU2, the U1, the SU2, the SU3, and people have explored those options and have not found anything that unifies all of the standard model in one big gauge group. Let's hold off on it just for time reasons. Okay, so while we're discussing the classical groups, let's consider the group of invertible linear operators that preserve the complex inner product on an n by n dimensional complex vector space. A natural generalization of preserving the inner product on a real vector space. And this is the unitary group, UN. So these group elements satisfy U dagger equals U inverse. And are unitary. Or thus unitary. And this UN is isomorphic to the group of n by n matrices with complex entries such that the Hermitian conjugate of this matrix is equal to the inverse of the matrix. UN corresponds to a symmetry transformation to a continuous symmetry transformation and is therefore a Lie group. I'm kind of blazing through just because of time. I apologize. For any U element of UN, we have again that the number 1 is equal to the determinant of the identity, which is the determinant of U inverse U. By the unitarity of U, this is the determinant of U dagger U. This is the determinant of U dagger multiplying the determinant of U. And so because the dagger is the commission as the transpose complex conjugated, this is the modulus squared of the determinant of U is equal to 1. So hence the determinant of U equals E to the I theta, or some theta in 0 to 2 pi. The subgroup of matrices with the determinant U equals 1 is called SUN. And what you worked out in the homework, or will work out in the homework, is that the dimension of UN is equal to n squared, and the dimension of SUN is equal to n squared minus 1. Okay, I think that's certainly a good stopping point for the moment. Let me pause there. Jack had a potential question.
Oh, I was just talking about.
Yeah. I figured it was, yeah. Good. I could always go on, but time does not permit it. Any last questions before we wrap up? All right, cool. I will stop recording. People are welcome to stick around for a few minutes longer. Thank you so much.